Welcome to Naradar Academy. In this video, we are going to discuss what is meant by interior of a set, few theorems about interior of a set, and then we are going to see how to find interior of a given set of real numbers. Okay, first let's start with the definition. A point P belong to S is said to be an interior point of a set S if there exists an epsilon greater than 0 such that the interval p minus epsilon to p plus epsilon is contained in S. Okay, so this is the definition. That means interior point means, see, S is a subset of R. A point P is said to be an interior point for S if there exists at least one epsilon for which the open interval, that is the neighborhood, p minus epsilon to p plus epsilon is completely contained in S. Okay, so interior point means what? The neighborhood, at least one neighborhood of the point must lie completely within the set. Okay, such a point is called what? Interior point. Okay, right. Actually, what do you mean by interior? Actually, the literal meaning is what? Which is lying inside, isn't it? Inside a set. So the same meaning also here. So if a point P is such that it has at least one neighborhood which is completely lying inside the set S, that point is called what? Interior point. And the collection of all interior points of a set is called interior of S, and the notation is int S or SO. Okay, so this is the definition. With this definition, let's start with theorem. Let S be any subset of R. Then R minus interior of S is equal to closure of R minus S. What do you mean by closure of a set? Closure is nothing but the collection of all adherent points of the set. What do you mean by adherent point? A point is said to be adherent point if every neighborhood of the point contains a point of S. Okay, so all these things I have uploaded in the previous video, so you can go through that video for getting a clear idea about closure. So here what we are going to prove in this theorem is R minus, that is the complement of interior is equal to closure of complement of the set. Okay, right. So for proving this theorem, first I am going to take a point, an arbitrary point P from R minus interior of S. Okay, so what do you mean by this? P belong to R minus interior of S means P is not a point of interior of S. Okay, P is not a point of interior of S. That means what? For every epsilon greater than 0, the neighborhood p minus epsilon to p plus epsilon is not completely contained in S. Okay, see, when will you say a point is in interior? For a point to be in interior, at least one of the neighborhood must be completely contained in S. In the opposite way, I am saying P is not in interior means for every epsilon. See, note this point, for every epsilon, whatever epsilon you take, that neighborhood p minus epsilon to p plus epsilon is not contained in S. Not contained in S means what? Some of the points, okay, at least some of the points are not in S, isn't it? That is, at least some of the points of p minus epsilon to p plus epsilon contains points of R minus S for every epsilon greater than 0. That is, for whatever neighborhood of P you take, some of the points in the neighborhood must lie outside S. Outside S means what? It is in R minus S. Okay, let me interpret the point again. That means for every epsilon greater than 0, P minus epsilon to P plus epsilon intersection R minus S is non-empty. Okay, so that is neighborhood intersection S set is non-empty means this point P is a adherent point for this set. What is this set? R minus S. So P is an adherent point for R minus S. Therefore P belong to closure of R minus S. Actually I have started with the point P in R minus interior of S, and finally I have arrived at P belongs to closure of R minus S. So if you take a point in this set and finally you bring that point belong to closure of R minus S. So both the sets are equal. That is, R minus interior of S is equal to closure of R minus S. Okay, then next theorem. Next we will see some of the remarks based on the above theorem. R minus closure of R minus S equal to interior of S. closure of S equal to R minus interior of R minus S, and R minus closure of S equal to interior of R minus S. If you want to write the proof for all these results, in the similar way you can proceed as before in the previous theorem. Okay, right. Now, next theorem, the interior of a set S contained in R is the largest open subset of S. That is the interior, no, collection of all interior points of a set. It is the largest open subset of S. So three things are here. In the first step, I am going to prove interior of S is a subset of S. First, I am going to prove interior is a subset of S. Next, I am going to prove it is an open subset. And then I am going to prove it is the largest open subset. Okay. So first, let me prove it is a subset of S. Now, let P belong to interior of S. Okay. That means what? At least for 1 epsilon greater than 0, the open interval P minus epsilon to P plus epsilon is contained in S. When this whole interval is contained in S, the point P definitely will be inside S only, no? So P belong to S. Therefore, interior of S is a subset of S. Okay, right. Next one, what I am going to prove? It is a open subset. So for proving a set is open, what you have to prove? That set is neighborhood for each of its points. Okay, I want to prove interior of S is open. For that I have to prove this set contains neighborhood for each of its points. Whatever point you take in interior of S, it must contain a neighborhood of that point. So let me take one point P belong to interior of S. So interior, it is an interior means what? For at least 1 epsilon greater than 0, P minus epsilon to P plus epsilon is completely contained in S. Okay, so if I take any point from this interval, if Q is any arbitrary point in this interval, then this set can be considered as a neighborhood for Q also, isn't it? Because Q is lying inside this interval, so this interval can be considered as a neighborhood for Q also, isn't it? Okay, so what can I conclude? Q belongs to interior of S. Q is an arbitrary point. So what do I conclude? Every point in this open interval P minus epsilon to P plus epsilon is also a point of interior of S. Therefore, all the points of this interval are lying in interior of S, isn't it? Therefore, P minus epsilon to P plus epsilon is completely contained in interior of S. That implies interior of S contains neighborhood for each of its points. That is, you take one point in interior of S and you have proved its neighborhood is contained in interior of S. That means every point's neighborhood is there in interior of S. That means it is an open set. Okay, so it's an open subset we have proved. Next we have to prove it is the largest open subset of S. So for that you take T be an open subset of S. Okay, that is T contained in S and T is open. What I have to prove? Interior of S is the largest open subset. So for that I have to prove T is contained in interior of S. So for proving that you take one arbitrary point P in T. So for given epsilon greater than 0, T is an open subset only we have taken, no. So for at least 1 epsilon greater than 0, P minus epsilon to P plus epsilon is contained in T because T is open. But T is a subset of S, no. So this will be contained in S also. So from this what do we conclude? P is an interior point for S. That means P belong to interior of S. So initially we have started with a point P in T and we have proved P belong to interior of S. Therefore, T is a subset of interior of S. So, whatever open subset of S you take, that is always contained in interior of S. That means interior of S is the largest open subset of S. Okay. Then, next theorem. This is something like a corollary for the previous theorem. A set S in R is said to be open if and only if interior of S equal to S. The proof is very simple. First, let us take S be open subset. Okay. Open subset of R. Then, but what we know in the previous theorem, interior of S is the largest open subset of S, no? So this S must be equal to interior of S. Conversely, let us take interior of S equal to S. What we have to prove? S is open. But we know interior of S is open. Therefore, S is also open. Okay. Then, next one theorem. The interior of a set S contained in R is the union of all open subsets of S. Okay. So, for that, let me take T equal to union of all open subsets of S. Okay, union of all C where C is a open subset of S. Then clearly interior of S is contained in T because yes, interior of S is the largest open subset of S, no. So definitely interior of S is also a member of T. Okay, so one side of the inequality is proved. Then next one is you look at C. C is the union of open sets, no. So union of open subsets is also a open subset. Therefore T is also open. But interior of S is the largest open subset, no. So T is contained in interior of S. So from these two inclusions we conclude T is equal to what? Interior of S. That is, interior of S is nothing but union of what? Union of all open subsets of S. Next, some of the results we'll see. Interior of empty set is equal to empty. Interior of R equal to R. If S is a subset of T, then interior of S is a subset of interior of T. And interior of S intersection T equal to interior of S intersection interior of T. And interior of S union T equal to contained in. Interior of S union T is contained in interior of S union interior of T. Next, find the interiors for the following sets. Now, for open interval 0 to infinity, the interior equal to the same thing. Okay, for half open interval minus infinity to 1, the interior is equal to minus infinity to open interval 1. So, for writing interior for any interval, you have to put the open interval because the corner points cannot be interior points. Okay, so you remember like this, interior point means what? Lying inside only, no? So, boundary points cannot be interior points. So, whenever you get an interval, you have to omit the boundary points by writing its interior. So, interior of minus infinity to closed interval 1 is equal to open interval minus infinity to 1. Next, interior of Q equal to empty set. Because no point is an interior point of Q. Because whatever rational number you take or whatever real number you take, if you consider any neighborhood or any open interval containing that point, that will contain infinitely many irrational numbers also. Therefore, Q is not Q is not a neighborhood for any of its points. So interior of Q equal to empty set. Similarly, for irrational numbers also, whenever you take any number, okay, that in any neighborhood for that number will contain infinitely many rationals and irrationals. Therefore, interior of R minus Q is also equal to what? Empty set. Then interior of any open interval equal to the interval itself. Okay, that is interior of minus 1 by n to 1 by n open interval is equal to the same set. Interior of any closed interval equal to the open interval a comma b. The corner points are not included. Okay, then interior of Z equal to empty because Z is what? Discrete set. No, discrete set has no what? Interior points. And interior of R equal to the full set R itself. Okay, right. That's all. Thank you.